All right. Thanks, Jan, and thanks, Aki, for the invite. And thanks, everyone, for attending this luncheon session. So I'll speak about the 6x12 large format for high-NA technology. So the agenda is quite simple. I'll take a few minutes and speak about the high-NA mask readiness. And then I will speak about what is 6x12. Some of you have attended some of the workshops, but some of you are new. So I'll explain what is 6x12 and why we need it. Like Jan said, I'll give an update on the workshops and the results and the progress. Then I'll talk about the topic of how real is this. And then I'll close with some of the ecosystems for the mask industry. But first of all, let's talk about the high-NA mask. You have seen many pictures of the high-NA scanner shipping into Oregon and other places. Steve Carson yesterday presented at the keynote about the two systems that are working in Oregon, printing wafers. And there's an opportunity for me to say that we also have the mask tooling for high-NA, and I've showed some pictures here. This is the multi-beam writer that is specialized for high-NA, the Ames tool, the high-NA EUV inspection tool, plus a number of other tools that make up the entire high-NA mask making line. And in the middle picture, I show the anamorphic high-NA process. This image here shows the CAD. I don't know if the lights can be dimmed a little bit, but you can see the features that are 8x and 1 axis. And when they go on the wafer, they shrink, and the other direction. And in this, this is the same feature, gets shrunk by, the 8x. And these are some of the images. And basically, we are the first in the world to make high-NA mask for high-volume production. And I'll show you a little bit how we do that. So the question came up yesterday in the conference, and somebody was asking how different is a high-NA mask from a 0.33 mask. And the answer was correct. It is an evolutionary process. We're not starting from scratch, but it is not the same. It's quite different. Fundamentally, you would start with the stack, and of course, the multi-layer stack that creates the Bragg mirror. Then we have the tantalum-based absorber. And in order for us to produce good results, we have to throw everything at high-NA. We've used up high-NA OPC. We use ILT, inverse lithography. We took advantage of the curvy, all the curvy SRAFs. All these are needed. And at the end of the day, we can produce the desired mask. And the primary purpose here is, with high-NA, you lose a little bit on the depth of focus. So the mask has to be better, the sub-resolution has to be better to compensate for the depth of focus degradation. Now, in addition to this, in the mask shop, primarily in the area of MPC, that's mask process correction, we use dose-based or pixel-based dose modulation in order to get the right features on the mask. We presented a paper on this last Bacchus. This is some of the more recent results. And a brand new process line. I mentioned the multi-beam 301, a new resist, high dose resist, a new etcher. At the end result is actually what speaks for itself. And this is the CD uniformity distribution on the 0.33 NA. And right next to it, you see the CD distribution on the high-NA process. And that's a phenomenal improvement that we were able to achieve. And so I talked at the beginning of the presentation, I spoke about high-volume manufacturing, and what does that mean? We define high-volume manufacturing as to be able to have a process day in, day out that produces the same mask, the same spec every time you do it, so our customer doesn't see any variability. But in addition to that, we need to maintain the error on the mask to less than 1 per million. If you cannot do that, then you cannot repair. And I've seen a lot of pictures in conferences where somebody does this once or twice. But in order to have a reliable manufacturing, you need to be able to do this day in, day out. And that's why I decided to show some of the images here. We have a 22 nanometer lines and spaces. These are 22 nanometer ISO and space on the same mask, on the same process, and with a failure rate of less than 1 in 10 million. So at this point, I can stop and let you enjoy your lunch and declare my presentation is done. But I will not do that. So now, let's talk about High-NA and the problem with High-NA. So about 10 years ago or so, when the designers were working on the High-NA machine, they faced a challenge. And the challenge is, as the NA increases, the NA of the mask also increases, and that's a problem. Because the NA of the mask is the High-NA divided by the magnification. So when you take that 0.55 now and divide it by 4x, then the angle, the NA of the mask increases. And when that happens, it disrupts the contrast. We suffer contrast, and when you have a contrast problem, because of the interference, you lose the advantage of the High-NA. So there is really no point in doing that. So they came up with the idea of enlarging the magnification to 8x. And ideally, they would have done 8 by 8, 8x in one axis, 8x in the other, and then make the mask 12 by 12. But that was not realistic, considering the difficulty it would be to make such a large mask. It will be thick, it will be hard to handle. And also, it's not necessary to be 12 in both axes. You only have the problem in the scan direction. And that's why anamorphic imaging came about, and you do 8x in one axis, but 4x in the other. Now, in doing so, the option of going to 6 by 12 also didn't exist. So they came up with the idea of cutting the field in half. And I think at the time, everybody in the industry agreed. I thought it was a great idea. And I bet you many of the people who agreed to this were thinking, 10 years from now, I'll be retired. Sure, you can cut the field in half, not a problem. And here we are today. So cutting the field in half causes you two issues. Number one, you lose the throughput. And number two, you have a stitching problem. If you have a large field, that requires a large die or a large chip. That requires 2 masks. And I don't remember who said this today, but somebody said, like, if you do multiple patterning with 0.33 NA, then you have more masks, because with high NA, you don't need to do double patterning. You don't need as many masks. But today you do, because you have to make an A and a B. And you expose one half, and then you expose the other half. And maybe I show you a little bit of animation to sort of explain this a little bit better. I have a few cases here, so bear with me. This is our traditional 0.33 NA exposure system. And this is our vision of the high NA. This is today's high NA, which is 2 masks, mask A and mask B. And this is the 6 by 12 mask that I'm pitching, and we've been working on for a while. And this case here is the case of a byproduct. If we actually do this for high NA, as a byproduct, we will get we'll get twice the real estate on the 0.33 NA. So a normal exposure, you have 1-to-1. And today, we have the first mask, and then the second mask. And of course, I want to point out this no-fly zone. You cannot put critical dimension features in that budding area. When we succeed in making 6 by 12, then the exposure would look something like this. And now the entire chip is scanned in one mask. And like I said, this can be propagated to the 0.33 NA, and you improve the throughput there as well. And that will give you 2 instances on the same mask, and that increases the throughput. So the argument is quite valid, and you can't just imagine something, you have to go and validate it with industry leaders and see if it makes sense. So I borrowed this from Mark Phillips, our fellow at Intel, and he presented this. He presented twice, actually. He presented in 23, and he had some estimates for the throughput. He was thinking about 10% to 40%. Now, in October last year, he came in and he upped his estimate, and he said it's going to be between 23% and 50%. And that further pushes on the argument that this is needed and it has real benefit. Also, at the last workshop in Monterey, we invited Sherlock, and he is one of the senior system engineers at ASML, and he provided more, I would say, mathematical data. And his argument was, I don't know if you can see all the details, I'll just give you the net. He basically says if we go to 0.55 NA and we go to 6 by 12, then we're going to be able to do 250 wafers per hour. And the same concept applies if you go to the 0.33, and that gets us to 450 wafer per hour. And these productivity numbers are extremely appealing to the industry, considering the cost of the scanner. I will not mention the cost, but I think many of you already know that. OK, so this is the workshop that we had in October. And yeah, I see a lot of people that I can recognize here. And if you need a high-resolution image, let me know. I think my friend from ASML is the one who took it with his big lens. So I think we can get much better resolution. And I think this was in response to the question is, how many of you think that this is useful and we should continue? And I think the message was, yes, this is very promising. We should continue, and we move on. But a few things came out of the workshop that I thought extremely important, and I want to point them out. Number one, we have definitely an industry momentum. 150 participants show up, 55 companies. Every single company that has anything to do with reticles, whether in the mask or in the fab or in the CAD area, everybody participated, everybody had a voice. Number two, we came to the conclusion that in as much as I talk about this as 6 by 12, in reality, it's 6 by 11.2. And why 11.2? Because the scanner today has the travel distance in the chamber to go 11.2. And when the ASML engineers ran the numbers, they found out that within the 11.2, we can actually do everything we want. And there's no need for ASML to go and do a major surgery on the expensive scanner. The other point I want to make is we all agreed that the thickness needs to be 0.25. And the reason for the thickness to be 0.25, so it's compatible with the 6 by 6. Today, 6 by 6 by 0.25, we would have liked the 6 by 12 to be 0.4 or 0.5, but it would make it difficult for the machine to be able to do both. And this is one of my requirement, is I'd like the machines to be able to do both. And I'll speak to that towards the end and why that is important. The other thing we did is we launched a couple of SEMI task force. SEMI has been extremely helpful and cooperative, and we're starting to get a lot of these logistics out of the way so the tool designers can all be working from the same spec sheet. All right. If you're a mask maker or in your mask making equipment, you should be very scared because everything to do with mask is red. Almost everything in the mask has to change, from blanks to code, the beam, etch, metrology, everything. Now, there's a little bit of work in the fab, but it's really within the area of litho. Of course, the scanner is going to be different. Mask inspection and handling will be different. The stockers will be different. But actually, reticle inspection may be the same, because once we make a reticle inspection in the mask shop, the same technology or practically the same tool goes into the fab. All right, these are some images from AGC. AGC did a lot of work, and we were looking at a few things. We were looking at sag, stress, and weight. And just for reference, this is the 6 by 6 by 0.25. Our goal is to match the green as much as possible. We toyed a little bit with 12-inch round, and then we looked at 12 by 6 or 6 by 12 with a 4-point contact, just like today. The mask today sits on 4 points. And you can see the sag and the stress is really too much to bear when we are talking about just 4 points, especially when we talk about 0.25. So we came up with the idea of having 6 points by bringing the 6 points of contact that allows and 0.25 thickness. Then now we're looking at numbers comparable to the 6 by 6. So this is the 6 by 12 from a sag point of view with respect relative to the 6 by 6. This is the stress. You can see that at 0.25, it's larger than the 6 by 6, but talking to the ASML engineers, the scanner today has many, many different corrections and many, many different ways to chuck that reticle, and they can compensate for that stress. And the weight is not so bad. We go from 0.7 to 1.4, so it's twice as heavy. It prompts us to do a little bit more automation in the mask shop, which honestly, we all need to do more automation in the mask shop anyway. Another thing I want to point out, at the workshop, we showed some examples to demonstrate that this thing is real. This is a blank from AGC on a Posetta box. And then this is a Gudon Smith pod. I had a meeting last week prior to the conference with Integras. They showed me a similar box, so they are also moving in that direction. This is my favorite. This is the pellicle, because every time we talk about 6 by 12, the pellicle, what happens to the pellicle? So these guys are working on CNT. The CNT pellicles are pretty decent. We asked them to make a 6 by 12, and they sure did. I don't know if my video will work. I'll try it. Yeah, see, it's a real pellicle. And this is just a picture of the demo table, and a lot of people just sort of hovered around it. And this work is important not only for like getting people energized and encouraged about it, but these blanks, we've been shipping them to other equipment makers so they can get started and get going with this. So if you look at the tools, I put the tools in sort of like a 3 classification, the tools in the mask shop. So we have the tools that have a moving stage and sort of like they work on a stripe basis, whether it's inspection, rider, metrology, the stage move in one axis, but the beam, whether it's laser or eBeam, is limited to a small swath. And for these tools, you just extend the stage in one axis, but all the accuracy associated with the head, whether it is writing or inspecting, it's sort of localized. And the chamber needs to grow only in one axis. Now, the more difficult ones are the tools that spin, like decoder, developer, cleaner. Those are more difficult. And how do you spin a rectangular shape? And it just happened that the size of this reticle doesn't quite fit in a 300-millimeter chamber. So we're quite worried about that. And then we have the stationary tools like the etchers and the Asher, bunch of others. And then we also have the pellicle, which I talked about a little bit. So we started working with the suppliers and try to see what we need to do to reduce the risk. And I'm just going to show a few of those suppliers or equipment makers. My favorite is Micronic, because there's 2 things. It's a great attitude. I mean, the Micronic guys first like, oh, you want to make a 6 by 12? Yeah, we can do it, no problem. Of course, because they make the masks for the flat panel industry. And they are used to the Hoya blanks. They are a meter by a meter by, I don't know what the thickness is, but they got to be pretty thick. So they went off, they took one of their machines, the SLX, came back with a design. These guys are ready to go. They're ready to give us a tool mid-26 for prototyping. and a real tool in 27. Now, why is this important? Because we need to put patterns on the glass. We need a tool that can put patterns. Alabite is laser writer quality patterns. We're not talking about 20 nanometer, but it's going to be good enough. 150 is good enough because we can get the blanks, we can put features on them, and then we can start doing work with the developer, the etcher, the cleaner, and so on. So having such tool come up early is really important for that. The other one I want to talk about is TEL. TEL took a very interesting approach, which is sort of the way I do business. They go after the most difficult problem first. Anybody can add cables and a computer and make the machine pretty. The issue is how to work on the most difficult thing, which is how do you coat properly a rectangular piece of glass. So they set up a test stand, and they started by taking wafers and cutting them to 6 by 12 or as close to it, and trying to see the resist uniformity and so on. Later, we started shipping them real masks, and they're doing the experiment real mask. And you see something here that is sort of counterintuitive in the sense that at high speed, you see worse uniformity than at low speed. I've always, in my head at least, I was thinking that if you spin it fast, then you're going to get better uniformity, but it's the other way around. So that kind of learning is important because when we go into the real machine, you retire some of that risk. You retire some of that unknown. And then the applied guys also get engaged and took a slightly different approach, but it's the same idea, is to take two 6 by 6 reticles and put them inside the chamber and start looking at the resist loss uniformity, the tantalum oxide etch uniformity, and so on. But it's basically the same concept. And all this learning will lead to a better chance that we're going to have real tools. All right, and I'll just speak a little bit about the standards. This is the standards committee. We looked at two things in the standards committee. We looked at the single pod and the dual pod. And if many of you mask makers like you've been around for a while and you see your mask shop grow over the years, we have one tool that likes the mask in this orientation, and another tool that likes the title in this direction, another one that likes it flipped. So throughout my entire mask shop, I have these little tools ahead of the machines that do the right orientation. And this is really good because now we're getting in front of it. Now we're saying which way we're going to go. And everybody agreed that we're going to go, I call it the long stroke. So the robot will have a long stroke in order to bring the mask in. And if you hear the word short side first, then it's about the same thing. It's just the short side first. But this work is really useful and helpful. All right, so I'll give you some economic arguments and try to close, because we can fantasize about technology if all we want. Unless there is an economic argument, we don't get anywhere. All right, so conclusion from the mask industry is yes, we can do it. And the degree of enthusiasm and difficulty varies from supplier to supplier, but in general, there are no showstoppers. We did a rough budgetary estimate what all these new tools are going to cost. And again, it depends on the supplier, but it's somewhere between 1.2x to 2x of a 6 by 6 tool. So the cost is not outrageous. It's sort of reasonable. All right, and what about ASML? Because if ASML cannot modify the scanner, then we cannot get anywhere. So ASML actually been warming up very nicely to this. I would say 3-4 years ago, they were like, oh, no, the mask industry can't do anything. But we turned that around. So ASML says, yep, they can do it, and possibly, they can do a machine that handles both, 6 by 12 and 6 by 6. We got some budgetary estimates. The scanner cost increase is not bad at all. It's actually reasonable. And if you look real hard at the ASML long-term roadmap, basically the message is productivity via 6 by 12 is the only way. We got to get to 6 by 12 to get the best productivity, because at some point, other parts of the machine, like the stage speed and so on, becomes an issue. So I think ASML is definitely encouraging us as an industry here to proceed with this. All right. Then how do we make this infrastructure affordable? And I'll share with you my thoughts. So we're going to the 1 nanometer regime. And just to get everybody oriented, Intel, we use the terms angstrom, 18, 14, 10A. So 10A is equivalent to the 1 nanometer. Today we're piloting 18A. We're doing masks and test chips for 18. And very soon we're going to be doing the 10A, which is in definition. So we're going to get there. And everybody is the same. I mean, other companies that compete with us are on the same trajectory. We have to get to the 1 nanometer node. Now, when we get to the 1 nanometer node, we're going to need a new tooling that are more accurate. Maybe I can take my 18A tools and push them to 14. But for sure, you cannot extend the tools to the 1. At the 1 nanometer node, we're going to have to get a better etcher. We're going to have to get a better beam. We're going to have to get a better developer. We're going to have to get better metrology. Because if you can't see the errors, then you can't fix them. So the idea is to have a dual tools that can do 6 by 6 and 6 by 12. If we buy all the tools that are 6 by 12 only, then we sunk all that capital, and we're going to wait a few years until we can have that 6 by 12 ready, and can't afford that amount of capital. Now, if we make the tools 6 by 6 or 6 by 12, then we can bring the tools in, put them in production at 6 by 6, start developing the 1 nanometer node. Maybe a couple of days a week, we do 6 by 12 experiments, but now we're getting our money back on that capital investment. And the same goes for the scanner. You don't want a scanner sitting there that only does 6 by 12. You really want to utilize it to make your normal production. Then people asked me, I said, OK, well, what about the cost? Honestly, the cost gets absorbed by the fabs. Like, I don't know how many years ago now, maybe like 7 or 8 years ago, people were complaining about the EUV mask cost and the EUV blank cost. And I always told them, when the fab needs EUV, they will pay. And now people are paying for the EUV mask without, they complain, but they're paying. So today, the EUV mask is roughly 8x the price of an optical mask. So the high-NA mask is more expensive. If it gives you 50% productivity on the scanner, why not? Then the whole industry benefits. All right, so final thoughts. Number one, we need the semiconductor industry healthy. We need people to buy GPUs, CPUs, communication. The more chips we sell, the better our industry is. So we need that wave we're on now to continue. And that will fund the wafer and the mask infrastructure. I think the scanner productivity argument is real, and we should pursue it. I didn't talk much about stitching, but there are a few papers in this conference that talk about the no-fly zone and how they're going to cut up the design. And I've talked to some customers that make large GPU chips. They really can't wait because they want to be able to put more silicon. I claim that this opportunity is unique. I think we need to intercept the 1 nanometer node. I think if we go off and spend our budget on 6 by 6 tooling for the 1 nanometer node, I don't know when we're going to be able to generate enough money to insert this at a later node. So my recommendation to everyone is please figure out a way to make it happen and look within your own company, just like Micronic did. No, Micronic. Yeah, Micronic. Just like Micronic did, and figure out how to do it and how to do it fast. and we'll figure out how to get a prototype in quickly and then be able to do a production one.